Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. The twin paradox: why space travel keeps you young. Two twins stand together on Earth, both 20 years old, identical in age and appearance, and one twin boards a spaceship that accelerates to nearly the speed of light, travels to a distant star, turns around and returns to Earth, while the other twin stays home. And when the travelling twin steps off the spaceship, expecting to greet their sibling who is the same age, they discover something shocking. The twin who stayed on Earth has aged 40 years and is now 60 years old, while the travelling twin has aged only 10 years and is now 30. And this asymmetric aging is not science fiction, but a genuine prediction of Einstein's special relativity, confirmed by countless experiments with atomic clocks and particle accelerators. And yet it seems paradoxical, because relativity also says that motion is relative, that there is no absolute reference frame, that the travelling twin could equally well say they were at rest while Earth moved away and then returned, and by this reasoning the earthbound twin should be younger, and so both twins should expect the other to be younger. And this contradictory expectation is the twin paradox, a puzzle that has generated confusion and debate since Einstein first proposed special relativity in 1905. Imagine watching the travelling twins' journey from Earth. You see the spaceship accelerate to 80% of light speed, and time dilation occurs. A clock on the spaceship runs slower than clocks on Earth, ticking at 60% of the normal rate. And this is not an illusion or a trick of observation, but a genuine physical effect. Time itself passes more slowly for objects in motion, and so during the 10 years of ship time that the travelling twin experiences, 16 years pass on Earth, and when the ship turns around and returns, another 16 years pass on Earth, while only another 10 years pass on the ship, and the total is 40 years on Earth and 20 years on the ship. And the asymmetry is real. The travelling twin really has aged less. Their biological processes ran slower, their heartbeats were slower, their thoughts were slower. Everything about them unfolded in slow motion from Earth's perspective, though from their own perspective, nothing felt different. Time seemed to pass normally, but less of it passed. Now consider the situation from the travelling twins' perspective, and here is where the paradox seems to bite. Because from the ship's viewpoint, Earth is the object in motion. Earth accelerates away, then turns around and comes back, and by the symmetry of relativity, the travelling twin might expect Earth clocks to run slower, might expect the earthbound twin to age less, and yet the prediction is the opposite, and the resolution is that the situation is not actually symmetric. The travelling twin accelerates, feels forces, experiences changes in velocity, while the earthbound twin remains in an inertial reference frame, floating freely in space, not accelerating, and this asymmetry breaks the apparent symmetry of the situation. Special relativity applies only to inertial frames moving at constant velocity, and the travelling twins' frame is not inertial. They accelerate when leaving, accelerate when turning around, and accelerate when stopping back at Earth. And these accelerations make the travelling twins' frame fundamentally different from the earthbound twins' frame. And general relativity, which handles accelerated motion, confirms that the travelling twin ages less. The accelerations cause additional time dilation effects that accumulate during the turnaround, and the overall result is that the travelling twin is younger. Visualize the journey on a space-time diagram. With time running vertically and space running horizontally, the earthbound twin's world line is a straight vertical line, moving forward in time but not in space, while the travelling twin's world line is a bent path, going up and to the right as the ship travels away, then bending at the turnaround point, then going up and to the left as the ship returns. And the key insight is that in space-time, the proper time experienced by an observer, the time measured by their own clock, is the space-time interval along their world line. And this interval is maximized for straight paths and minimized for bent paths, exactly the opposite of spatial geometry, where straight lines are the shortest distance. And so the bent world line of the travelling twin corresponds to less elapsed time. They experience fewer years because their path through space-time is longer in space but shorter in time. And this is not a matter of perspective or coordinate choice, but a geometric fact about space-time, an invariant quantity that all observers agree on. The paradox has been tested experimentally, not with human twins but with atomic clocks in the Hafele-Keating experiment. In 1971, atomic clocks were flown around the world on commercial airliners and compared with clocks that remained on the ground, and the flying clocks showed less elapsed time, exactly as relativity predicted. The effect was tiny, measured in nanoseconds, because the planes were slow compared to light speed, but it was measurable and confirmed the theory, and similar experiments have been done with clocks on satellites, with GPS systems which must account for time dilation to function accurately, with particles in accelerators whose lifetimes are extended by time dilation. And in every case, the predictions of relativity are confirmed. Moving clocks run slow, and the effect is real and cumulative. The twin paradox also raises questions about space travel and the possibility of reaching distant stars. Because time dilation means that from the perspective of travellers on a fast spaceship, the journey to a star 10 light-years away need not take 10 years. If the ship travels at 99% of light speed, the travellers experience only about 1.5 years of travel time. The distance contracts in their frame. They see the universe compressed along the direction of motion, and they cross the 10 light-years in a fraction of the time it would take at lower speeds, and so interstellar travel is theoretically possible within human lifetimes, at least from the traveller's perspective. Though when they arrive home, they will find that decades or centuries have passed on Earth, their friends and family aged or dead, and this asymmetry, while not a logical contradiction, creates a deep emotional and philosophical tension. The travellers experience only a few years, but return to a world that has moved on without them. Some people respond to the twin paradox by rejecting relativity, by insisting that time is absolute, that both twins must age the same amount, that the theory must be wrong. But this response ignores the overwhelming experimental evidence, the thousands of confirmations in particle physics, astrophysics, and technology. The fact that relativity is one of the most thoroughly tested theories in all of science, and the predictions have never failed. And so the paradox is not a refutation of relativity, but a counterintuitive consequence that we must accept. And the strangeness of the result reflects the strangeness of the universe, the fact that time and space are intertwined, that time is not absolute but relative, that duration depends on motion, and that the universe operates according to rules that defy everyday intuition. The twins stand together again, one young and one old, and the younger twin has travelled through space and time, has experienced the compression of years into months, has returned to find the future arrived, and the paradox is resolved. There is no contradiction, only an asymmetry. The travelling twin accelerated, and the earthbound twin did not. And this difference explains everything, makes the situation non-symmetric, removes the paradox, and yet the strangeness remains. The fact that time is not fixed, that motion affects aging, that twins can end up different ages by taking different paths through space-time. And the twin paradox endures as a teaching tool, as an illustration of relativity's most counterintuitive predictions, as a thought experiment that has become reality through atomic clocks and particle decays, and as a reminder that the universe is stranger than common sense suggests, that time is not what we thought it was, and that the path you take through space-time determines how much time you experience, how much you age, how much life you live. And the travelling twin, younger by decades, stands as proof that Einstein was right, that time dilation is real, and that space travel, if we ever achieve the speeds required, will make astronauts into time travelers, moving forward into Earth's future while aging only slightly themselves. And the paradox, resolved but never fully domesticated, remains a monument to the weirdness of relativity and the malleability of time. The white crow paradox, when one exception destroys everything. The statement "all crows are black" is a universal generalization, claims that every member of a class has a certain property, and to confirm this hypothesis, we observe crows, find black ones, and each observation of a black crow provides some evidence that all crows are black. And as the observations accumulate, as we find hundreds or thousands of black crows and no non-black ones, our confidence grows. The hypothesis seems increasingly well supported, and this is standard inductive reasoning, generalizing from observed to unobserved cases, and yet there is an asymmetry, a striking difference between confirmation and refutation, because while confirming a universal generalization requires many observations, observing instance after instance, refuting it requires only one, requires finding a single counterexample, a single white crow, and this one observation destroys the hypothesis completely, shows definitively that not all crows are black, and this asymmetry between confirmation and refutation is sometimes called the white crow paradox, or the black swan problem, named for the discovery of black swans in Australia, which refuted the European belief that all swans are white, and the paradox highlights the logical asymmetry between universal and existential claims, between all and some, and raises questions about the rationality of holding universal beliefs based on limited evidence. Imagine searching for crows, observing thousands of them, recording their colors, finding only black crows, never seeing any crow that is not black, and based on this evidence concluding that all crows are black, and this inference seems reasonable, seems justified by the evidence, and yet it is logically vulnerable because it only takes one white crow, one single observation to prove the inference wrong, to show that despite thousands of confirming instances, the generalization was false. And this vulnerability is not unique to the crow hypothesis, but characterizes all universal generalizations, all claims of the form, all X are Y, and it raises the question of whether we should believe such generalizations at all, whether induction can ever justify universal claims, or whether we should limit ourselves to weaker claims, like all observed crows are black, or most crows are probably black, claims that cannot be refuted by a single counterexample. Visualize the logical space with confirmation as a gradual process, slowly accumulating evidence, moving toward but never reaching certainty, and refutation as instantaneous, a single observation that immediately establishes falsity. And this asymmetry is fundamental to the logic of universal and existential quantification, because to prove all crows are black requires checking every crow, which is impossible if there are infinitely many crows or even just too many to observe, while to prove some crows are not black requires finding only one. And so existential claims are verifiable but not falsifiable, can be proven true but not proven false, while universal claims are falsifiable but not verifiable, can be proven false but not proven true. And this asymmetry shapes scientific practice, shapes how we test theories, and Karl Popper built an entire philosophy of science around it, arguing that scientific theories should be universal claims that are falsifiable, that science progresses not by confirming theories, but by attempting to refute them, and theories that survive refutation attempts are corroborated though never confirmed. The white crow paradox connects to the problem of induction, to Hume's challenge, because induction moves from observed instances to unobserved generalizations, from particular to universal, and this move is never logically justified, can never guarantee that the conclusion is true even if all premises are true, and the possibility of a white crow, the possibility that the next observation will refute the generalization, is always present, can never be eliminated, no matter how many confirming instances we have observed. And this makes universal generalizations perpetually tentative, perpetually vulnerable. And some philosophers conclude that we should never fully believe them, should always maintain some doubt, should treat them as useful working hypotheses, rather than as established truths. The paradox also raises questions about the psychology of belief, about why we do believe universal generalizations despite their vulnerability, about why finding thousands of black crows leads us to believe that all crows are black, even though we know this belief could be refuted tomorrow by a single white crow. And the answer involves practical reasoning, involves the need to act and make decisions based on limited information, involves the fact that treating all crows as black, until proven otherwise, is useful, allows us to make predictions and navigate the world, and the cost of being wrong, of encountering a white crow, is usually low, does not justify the cognitive burden of maintaining constant skepticism. And so we believe universal generalizations not because they are logically justified, but because they're practically useful. Because acting as if they are true works well enough most of the time. The asymmetry between confirmation and refutation has been used to argue for various methodological principles. Popper's falsificationism says scientists should focus on trying to refute theories rather than trying to confirm them, should design crucial experiments that could show theories wrong, should prefer theories that make bold predictions that could easily be falsified. And this methodology treats the asymmetry as central, builds scientific method around the ease of refutation compared to the difficulty of confirmation. Though critics argue that Popper's philosophy does not match actual scientific practice, that scientists do seek confirming evidence, do not merely attempt refutation, and that confirmation and refutation both play roles in science, are complementary rather than opposed. The white crow appears rare and shocking, and the hypothesis that all crows are black crumbles instantly. Years of observations rendered irrelevant by a single exception, and this dramatic reversal, this sudden collapse of belief, illustrates the fragility of universal generalizations, the precariousness of inductive inference, and the paradox is not that refutation is easy, but that we believe universal generalizations at all given how easily they can be refuted, given that we can never observe all instances, given that the next observation might always be the white crow that destroys our confidence. And yet we do believe, we do generalize, we do infer from observed to unobserved, because we must. Because thinking and acting require going beyond immediate experience, require making assumptions about regularity, about patterns continuing, about the unobserved resembling the observed, and the white crow paradox stands as a reminder that these assumptions are always vulnerable, always tentative, always subject to refutation by new evidence, and that science progresses not by establishing certainties but by proposing hypotheses that survive testing, that withstand attempts at refutation, that continue to work until they do not, and the search for white crows continues. The search for exceptions, for counterexamples, for anomalies that challenge generalizations, because finding them is how we learn, how we improve theories, how we discover that what we thought was universal is merely local, that what we thought was necessary is merely contingent, and the white crow paradox endures as a lesson about the limits of induction, about the asymmetry between proof and disproof, and about the tentative nature of all empirical knowledge. Buridan's ass. When perfect balance creates perfect paralysis. A donkey stands exactly halfway between two identical bales of hay, equidistant from both, and the donkey is hungry, equally attracted to both bales, and both bales are identical in size, quality, freshness, and appeal, and there is no reason to prefer one over the other, no difference that would make choosing one more rational than choosing the other. And according to the principle of sufficient reason, the idea that every choice must have a reason, that rational action requires a reason to prefer one option over alternatives. The donkey cannot choose because choosing either bale would be arbitrary, would be action without sufficient reason, and so the donkey stands paralyzed, unable to move toward either bale, and eventually starves to death despite being surrounded by food. And this is Buridan's ass, a thought experiment in medieval philosophy, named after Jean Buridan, though the paradox predates him, and it illustrates a problem with certain models of rational choice, shows that if rationality requires sufficient reason for every choice, then perfect symmetry creates paralysis, creates situations where rational action becomes impossible. Imagine the donkey's perspective, looking left at one bale, looking right at the other, evaluating, comparing, and finding them perfectly equal. No basis for preference, no reason to go left rather than right or right rather than left. And the principle of sufficient reason says that to act rationally, the donkey needs a reason, needs something that makes one option better. And in the absence of such a reason, the donkey should not act, should remain neutral, should not arbitrarily favour one identical option over another. And so the donkey stays in place, and the bales remain equidistant, and time passes, and hunger grows, but still no reason emerges to break the symmetry. And the donkey, committed to rational decision-making, committed to acting only when there is sufficient reason, cannot move, and the commitment to rationality becomes a death sentence. The paradox challenges the principle of sufficient reason, challenges the idea that rational action always requires a reason to prefer one option over alternatives. Because in situations of perfect symmetry, there is no such reason, and yet acting is better than not acting. Choosing either balo is better than choosing neither, and survival requires breaking the symmetry. Somehow requires choosing arbitrarily, and if arbitrary choice is allowed, then the principle of sufficient reason is false, is not a requirement of rationality, and if arbitrary choice is not allowed, then rationality becomes self-defeating in symmetric situations, becomes a principle that prevents beneficial action, and neither option is attractive. Neither preserves our intuitions about what rationality requires. Visualize the situation as a balance, perfectly level, with equal weights on both sides, and the donkey as the fulcrum, unable to tip in either direction because the forces are equal. And tipping requires an imbalance, requires one side to outweigh the other, but no such imbalance exists, and so the balance remains level, and the donkey remains centered. And the metaphor captures the paralysis, the inability to move, when reasons are perfectly balanced, when no consideration favors one option over another. One response to the paradox is to deny that such perfect symmetry ever occurs in reality, to argue that there are always small differences, imperceptible perhaps, but sufficient to break ties. One bale is slightly closer or slightly greener, or catches the light differently. And even if these differences are too small to consciously notice, they provide sufficient reason for the unconscious decision-making processes that guide action, and so real donkeys never face perfect symmetry, never actually starve between identical bales, because nothing in nature is perfectly identical. And the paradox is a thought experiment that does not correspond to any actual situation. And while this may be true for physical objects, the paradox still applies to abstract choices, where perfect symmetry can be stipulated, and so the response avoids the real problem rather than solving it. Another response is to modify the principle of sufficient reason to allow arbitrary choice in symmetric situations, to say that rationality requires reasons to prefer one option over another when such reasons exist, but when options are genuinely equal, then arbitrary choice is rational, is indeed the only rational response. And in cases of perfect symmetry, choosing randomly is not irrational, but is the rational thing to do. And the donkey should flip a mental coin, should pick arbitrarily, should recognize that in the absence of reasons to distinguish between options, any choice is as good as any other, and making an arbitrary choice is better than making no choice. And this response preserves rationality while allowing action in symmetric cases. but it requires weakening the principle of sufficient reason, requires admitting that not all rational actions have reasons, that sometimes the rational thing is to act arbitrarily. A third response appeals to higher order considerations, argues that even when two options are equally good in terms of immediate outcomes, they may differ in terms of meta-level features, and the donkey should consider not just which bale to eat, but also principles of decision-making, and there are good reasons to have a policy of breaking ties somehow, perhaps always choosing the left option in symmetric cases, or always choosing randomly, and having such a policy provides sufficient reason to choose even when the options themselves provide no reason. And the donkey who has adopted the policy of going left in symmetric situations has a reason to go left. The reason is not that the left bale is better, but that the policy says to go left. And this preserves sufficient reason at a higher level while allowing action at the object level. But it raises questions about where the higher level policy comes from, whether adopting the policy itself requires sufficient reason, and whether we have just pushed the problem back one level without solving it. The paradox also connects to debates about free will and determinism, because if every choice requires a sufficient reason, a cause that explains why that choice was made rather than another, then in situations of perfect symmetry, no choice can be made. And yet humans and animals do make choices in such situations, do break ties, and this suggests that not all choices are determined by reasons, that there is some indeterminacy, some capacity for arbitrary choice, and libertarians about free will embrace this, argue that free will requires the ability to choose without sufficient determining reasons, requires that agents can tip the balance even when reasons are equal, but compatibilists and determinists argue that apparent symmetry is always broken by hidden factors, by unconscious preferences or random neural fluctuations, and what looks like arbitrary choice is actually determined by factors we do not consciously access. The paradox appears in practical contexts involving decision-making under uncertainty, where multiple options have equal expected value, and decision theory must specify what to do in such cases. And most theories say to choose randomly, to treat equal value options as interchangeable. And this is the rational response, but it requires abandoning the strong version of sufficient reason, requires accepting that rational choice sometimes is arbitrary choice, and this has implications for ethics and policy, for situations where multiple actions are equally good, where no moral consideration distinguishes between them. And in such cases, acting is better than paralysis, and any permissible action can be chosen without need for further justification. The donkey stands motionless, hunger gnawing, hay on both sides, and the commitment to sufficient reason becomes a trap, becomes a principle that prevents survival, and the paradox remains, challenging rationality, forcing recognition that reason has limits, that symmetry creates problems, that pure rationality cannot solve, that arbitrary choice, far from being irrational, is sometimes the only rational response. And Buridan's ass endures, starving between equal bales, a symbol of the perils of excessive rationality, of the dangers of demanding reasons when none exist. And the paradox persists as a reminder that action requires more than reason, requires the capacity to break ties, to choose when choices are equal, to act despite the absence of sufficient reason. And rational agents, whether donkeys or humans, must possess this capacity or risk paralysis, risk standing frozen while opportunities pass and the ass remains. Hypothetical but instructive, teaching that rationality is not just about having good reasons, but also about knowing when reasons run out and arbitrary choice must begin. Yablo's paradox. In 1993, the philosopher Stephen Yablo introduced a paradox that seemed impossible, a self-referential contradiction that contains no self-reference at all, a loop without a loop. And this paradox has troubled logicians ever since because it challenges the assumption that all semantic paradoxes arise from statements referring to themselves. Imagine an infinite sequence of sentences, each one numbered, and each sentence says the same kind of thing. Sentence 1 says for all sentences after this one, at least one of them is false. Sentence 2 says for all sentences after this one, at least one of them is false. Sentence 3 says the same, and so on forever, each sentence making a claim about all the sentences that come after it, but never referring to itself or to any sentence that comes before. Now consider whether sentence 1 is true. If it is true, then at least one sentence after it must be false. So sentence 2 or 3 or some later sentence must be false. But sentence 2 makes the same claim as sentence 1, just shifted down the sequence. So if sentence 2 is false, then all sentences after it must be true. But sentence 3 says at least one sentence after it is false, which contradicts the idea that all sentences after sentence 2 are true, and so sentence 2 cannot be false. And the same reasoning applies to every sentence in the sequence. None of them can be false without contradiction, which means all of them must be true. But if all of them are true, then sentence 1's claim that at least one sentence after it is false must itself be false, and so we arrive at a contradiction without any sentence ever referring to itself. The paradox is startling because it was long believed that self-reference was the root of all semantic paradoxes, that statements like "this sentence is false" create problems precisely because they loop back on themselves. But Yablow's paradox suggests that infinite chains of reference can generate the same kind of contradiction, even when each individual sentence only points forward, never backward. Some philosophers argue that Yablow's paradox is secretly self-referential after all, that the infinite sequence as a whole refers to itself in some implicit way, or that each sentence indirectly refers to itself through the mediation of the sentences that follow. But others insist that the paradox is genuinely non-self-referential, that it reveals a new kind of logical pathology that cannot be explained by the old models. The paradox has deep implications for theories of truth, because if self-reference is not necessary for paradox, then many proposed solutions to the liar paradox and related problems must be reconsidered, and new strategies must be developed to handle infinite structures that generate contradiction through endless forward reference, rather than immediate loops. Some logicians suggest that the paradox arises because we are treating an infinite sequence of statements as if it were a completed whole, and that in a finite or constructive framework, the paradox would dissolve, while others embrace infinitary logic and try to develop formal systems that can accommodate Yablow's structure without collapsing into inconsistency. The paradox also connects to issues in recursion theory and computer science, where infinite loops and non-terminating processes can exhibit similar behavior, generating contradictions or undefined results, without any single step referring back to a previous one. Yablow's paradox stands as a reminder that infinity is strange, that logic stretched across endless sequences behaves in ways that defy intuition, and that the boundaries of coherent thought may be more fragile than we imagined, that even without the familiar twist of self-reference, language and logic can still tie themselves into knots from which there is no escape. Grandy's series, when adding numbers, forever gives multiple answers. A simple mathematical series begins with 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing forever without end, alternating between adding 1 and subtracting 1. And the question emerges, what does this infinite sum equal? What value does it approach as more and more terms are added? And the paradox is that different methods of calculation give different answers, each seemingly valid, each following mathematical rules, yet reaching contradictory conclusions. And this is Grandy's series, named after the Italian mathematician Guido Grandi, who studied it in the early 18th century. And the paradox reveals fundamental questions about what it means to sum an infinite sequence, about whether all infinite series have definite values, and about the limits of algebraic manipulation when dealing with infinity. Consider the series visually. Imagine a number line where you start at 0, then move 1 unit to the right to reach 1, then move 1 unit to the left back to 0, then 1 unit right to 1 again, then 1 unit left to 0, and this pattern continues forever, oscillating between 0 and 1, never settling down, never approaching a limit in the traditional sense, and so, from this perspective, the series does not converge, does not have a sum. The partial sums bounce between 0 and 1 eternally and never stabilize. But now consider a different approach. Group the terms in pairs, taking 1 minus 1 as the first pair, which equals 0, then 1 minus 1 as the second pair, also 0, and so on. And the series becomes 0 plus 0 plus 0, continuing forever, and the sum of infinitely many zeros is 0. And so by this grouping method, the series equals 0. And this seems like a valid manipulation. Grouping terms is a standard algebraic operation, and yet it produces a definite answer where the oscillating view produced no answer. Now consider another grouping. Start by leaving the first one alone, then group all subsequent pairs, so the series becomes 1 plus the quantity negative 1 plus 1, then the quantity negative 1 plus 1, and so on. And each grouped pair equals 0. So the series becomes 1 plus 0 plus 0 plus 0, continuing forever. And this equals 1. And so by this different grouping, the series equals 1 instead of 0. And both groupings seem legitimate. Both use standard algebraic rules, yet they produce different answers, 0 and 1. And this is the heart of Grandi's paradox, that the series is sensitive to how it is manipulated, that rearranging or regrouping terms changes the result. And this suggests that the series does not have a well-defined sum in the ordinary sense. Mathematicians have developed sophisticated tools to handle divergent series, like Grandi's, and one approach is Cesaro summation, which assigns values to series by averaging the partial sums. And for Grandi's series, the partial sums are 1, 0, 1, 0, 1, 0, continuing to alternate, and the average of the first n partial sums approaches 1/2 as n grows large, because roughly half the partial sums are 1 and half are 0. And so by Cesaro summation, Grandi's series equals 1/2, and this method produces yet another answer, neither 0 nor 1, but the midpoint between them. And this answer has a certain aesthetic appeal. It represents the average behavior of the series, the value around which it oscillates, and it can be justified by analogy to functions. If you consider the geometric series 1 minus x plus x squared minus x cubed and so on, which converges to 1 over 1 plus x for absolute value of x less than 1, and you plug in x equals 1, you get 1 over 2. And so in some extended sense, Grandi's series can be said to equal 1/2. The paradox reveals that divergent series do not have sums in the way convergent series do, that assigning values to them requires making choices about what summation method to use, and different methods give different results. And there is no single correct answer, but rather a family of possible values, depending on the context and the techniques employed. And this multiplicity is not a flaw in mathematics, but a feature, a recognition that infinite sums are more subtle than finite sums, that operations that work for finite cases can break down or become ambiguous when extended to infinity. Grandi's series appears in physics and engineering, in Fourier analysis, where oscillating sums arise naturally, in quantum field theory, where divergent series are regularized using techniques similar to Cesaro summation, and in signal processing, where alternating patterns must be analyzed. And in these applications, the choice of summation method is guided by physical considerations, by what gives useful predictions, by what aligns. With experimental results, and the paradox becomes less troubling, less a contradiction, and more a reminder that mathematical tools must be adapted to fit the problem, that formal manipulation must be tempered with judgment about what makes sense in context. The series also appears in philosophical discussions about infinity, about whether infinite processes can be completed, about whether the phrase, sum of infinitely many terms, has a determinate meaning or depends on conventions and choices. and Grandi's series suggests the latter, that infinity introduces ambiguities that finite mathematics avoids, that extending concepts from finite to infinite is not automatic but requires care, requires new definitions, requires acceptance, that some questions have multiple answers or no answer at all depending on how they are framed. Imagine watching someone walk back and forth on a path, taking one step forward, then one step back, then one step forward, then one step back, forever without stopping, and you are asked where they end up, and the answer is that they do not end up anywhere. They continue oscillating. But if you ask where they are on average, you might say they are halfway between the two endpoints. And if you ask where they are after an even number of steps, you say at the start, and after an odd number, you say one step forward, and none of these answers is wrong. Each captures a different aspect of the situation, and Grandi's series is similar. Different questions about the series have different answers, and the paradox arises from expecting a single answer when the situation is inherently ambiguous, when the infinite oscillation resists reduction to a single number. The series continues, 1 minus 1 plus 1 minus 1, terms alternating forever, and the sum is 0 or 1 or 1/2 depending on how you calculate it, depending on what method you use, depending on what question you're really asking. And the paradox endures, a simple series that exposes deep issues about infinity, about summation, about the limits of algebraic manipulation, and about the need for careful definitions when dealing with infinite processes. And Grandi's series remains a teaching tool, a cautionary tale, a reminder that infinity is subtle, that divergent series require special handling, and that mathematics is not just calculation, but interpretation, not just following rules, but understanding when rules apply and when they break down. And the series oscillates, forever unresolved, forever producing different answers, and the paradox persists, elegant and instructive, a monument to the strangeness of infinity and the care required when extending finite concepts to the infinite realm. Goodman's GRU paradox. When emeralds turn blue at midnight, a philosopher invents a new color term, GRU, and GRU is defined as follows. An object is GRU if it is observed before time t and is green, or if it is not observed before time t and is blue, where t is some future date, perhaps January 1st of next year. And this definition is strange, is artificial, combines observation and time in a way that ordinary colour terms do not. But the definition is precise, is perfectly clear. And now the philosopher considers emeralds and notes that all emeralds observed so far have been green. And these observations support the hypothesis all emeralds are green. And the same observations also support the hypothesis all emeralds are GRU, because all observed emeralds satisfy both descriptions. They are green, which means they are GRU up to time t, and both hypotheses are equally well supported by the evidence. Both fit all observations perfectly, and yet the two hypotheses make different predictions about the future. The first predicts that emeralds examined after time t will be green. The second predicts they will be blue. And so we have two hypotheses, equally supported by evidence, making opposite predictions. And the question is, which hypothesis should we believe? Which generalization should we project into the future? And Nelson Goodman poses this as a problem about projectability, about which predicates can legitimately be used in inductive inferences. And this is the GRU paradox, also called Goodman's new riddle of induction, a puzzle that shows that not all evidence-supported hypotheses are equal, that some predicates are projectable and others are not, and the challenge is to explain what makes green projectable and GRU not, what distinguishes legitimate from illegitimate generalizations. Imagine living in a world where emeralds are GRU, where all emeralds observed before time t are green, but all emeralds examined after time t are blue. And from the perspective of someone before time t, this is indistinguishable from a world where emeralds are simply green. All observations are the same, and yet the two worlds are radically different. will diverge dramatically after time t, and the puzzle is that evidence accumulated before t does not distinguish between these possibilities, does not tell us which world we inhabit, and so induction alone cannot determine which hypothesis to accept, cannot tell us whether emeralds are green or GRU. And this reveals that induction requires more than just fitting evidence, requires principles about which predicates are projectable, which generalizations are legitimate. And these principles cannot themselves be justified inductively without circularity. Visualize the timeline with time t marking a boundary, and on one side of the boundary, all observed emeralds are green. And the question is what happens after the boundary. Do emeralds remain green, or do they become blue? And the hypothesis, all emeralds are GRU, says they switch colours. But this switching is built into the definition of GRU, is a feature of how the predicate is defined rather than a feature of emeralds themselves. And this reveals something important, that the GRU hypothesis is gerrymandered, is artificially constructed to fit past observations while making a different prediction about the future. And our intuition is that such gerrymandered hypotheses should not be projected, should not be taken seriously, but explaining why requires articulating a principle that distinguishes natural from gerrymandered predicates. Goodman's own solution appeals to entrenchment, argues that green is projectable because it has been used successfully in many past inductions, has become entrenched in our language and our theories, while GRU is a newcomer, is defined artificially, has no history of successful projection, and so we should prefer green over GRU, not for any logical reason, but for pragmatic reasons, because green has proven its worth. And this solution ties projectability to linguistic and scientific practice, makes it a matter of history rather than logic. And some find this unsatisfying, find it too relativistic. But Goodman argues that there is no deeper justification available, that entrenchment is as good as justification gets for inductive inference. Another response argues that GRU is not a genuine predicate, is not natural, because it is defined in terms of observation and time, includes reference to specific moments and observers, and genuine properties should be observer-independent, should not change based on when or whether they are observed. And green is natural in this sense, refers to a real property that objects have regardless of observation, while GRU is artificial, is defined through disjunction and reference to observation, and so only natural predicates are projectable. And this solution requires explaining what makes a predicate natural, what distinguishes genuine properties from artificial constructions. And this leads to metaphysical questions about the nature of properties, about whether naturalness is objective or conventional. A third response from a Bayesian perspective argues that GRU hypotheses are less probable than green hypotheses given reasonable priors, because GRU hypotheses postulate discontinuities, postulate that properties change suddenly at arbitrary times, and such discontinuities require explanation, require reasons, and in the absence of such reasons we should assign low prior probability to GRU hypotheses. And so while GRU fits the evidence as well as green, GRU is less probable overall because of its lower prior, and this solution appeals to simplicity and parsimony, treats continuous properties as more probable than discontinuous ones, and explains projectability in terms of prior probabilities rather than entrenchment or naturalness. The GRU paradox also reveals that the problem of induction is deeper than Hume recognized, because Hume worried about justifying any inductive inference, about showing that the future will resemble the past. But even if we accept induction, we face Goodman's problem. We must choose which respects the future will resemble the past, must decide which predicates to project, and different choices lead to different predictions. And there is no algorithm, no mechanical procedure that tells us which predicates are projectable, which generalizations are legitimate. And so induction requires judgment, requires background knowledge, requires engagement with the actual practice of science rather than pure logical analysis. The paradox extends beyond emeralds and colours to any inductive inference, to all attempts to generalize from observed to unobserved cases, because for any pattern we observe, for any regularity we find, there are infinite GRU-like predicates that fit the pattern up to now, but diverge in the future, and choosing between these predicates cannot be done on evidential grounds alone, requires additional principles, requires distinguishing projectable from non-projectable predicates, and every scientific theory makes such choices, implicitly assumes that certain predicates are natural and others artificial, and Goodman's paradox makes these assumptions explicit, forces recognition that induction is not just about fitting evidence, but about choosing the right vocabulary, the right predicates, the right way of carving up the world. The clock approaches time t, and emeralds remain green, as they always have been, and the GRU hypothesis is refuted, is shown to have been wrong, but before time t, the evidence supported GRU as much as green, and this shows that evidence alone was insufficient, that something beyond evidence guided our preference for green, our confidence that emeralds would remain green rather than turning blue, and that something is what Goodman's paradox investigates, what it challenges, used to articulate, and the paradox remains not fully resolved, not answered by any single theory that satisfies everyone, but persistent as a challenge to theories of induction, a test case for accounts of scientific reasoning, and a reminder that generalizing from experience requires more than logic, requires substantive assumptions about the world, about which properties are real and which are artificial, about which patterns will continue and which will break. And these assumptions cannot be justified inductively without circularity, cannot be proven logically without begging the question. And so induction rests ultimately on judgment, on practices that have proven successful, on entrenchment or naturalness or simplicity. And Goodman's GRU paradox reveals this foundation, exposes the principles we rely on but cannot fully justify. And the paradox endures as one of the most important problems in philosophy of science. McTaggart's paradox of time, why past, present and future are contradictory. A philosopher named J.M.E. McTaggart constructs an argument attempting to prove that time is unreal, that temporal distinctions are contradictory, that past, present and future cannot coexist, and the argument begins by distinguishing two ways of thinking about time. The A series, which orders events as past, present or future, and the B series, which orders events as earlier than or later than each other. And McTaggart argues that the A series is essential to time, that change requires events to move from future to present to past, that without this passage, without the A series, there is no real time. But the A series is contradictory, generates logical problems, and therefore time is unreal, is an appearance generated by our temporal perspective, but does not correspond to ultimate reality. And this is McTaggart's paradox of time, one of the most famous and most controversial arguments in the philosophy of time, an argument that has shaped all subsequent debates about the nature of time, about whether time is real or illusory, about whether the passage of time is objective or subjective. Imagine time as having two aspects: the A series aspect where events are classified as past, present or future, where we say the meeting is future, is happening now in the present, was past yesterday, and events change their A series position, move from future to present to past, and this movement is time's passage, is what makes time dynamic. And the B series aspect where events are ordered as earlier or later, where we say the meeting is later than breakfast and earlier than dinner, and these B series relations are fixed, do not change. The meeting is always later than breakfast regardless of when we consider it. And McTaggart argues that the A series is essential for real time, that the B series alone is not sufficient, that time requires passage, requires events to change from future to present to past, but the A series is contradictory, and so time is impossible, is unreal. The paradox emerges from the fact that A-series properties are contradictory. Every event is past and present and future. The meeting is future before it occurs, is present when it occurs, is past after it occurs. And so the meeting has all three properties, is past and present and future. And these properties are incompatible, cannot all be instantiated by the same event. And so the A-series generates contradiction. And the standard response is to say that events have A-series properties at different times. The meeting is future at earlier times, present at its time of occurrence, past at later times. And this seems to resolve the contradiction by indexing A-series properties to times. But McTaggart argues this does not help, because now we must ask whether the times themselves are past, present, or future. And the same problem recurs. If the time at which the meeting is future is itself past, then the meeting is past and future, and contradiction remains. And indexing to times does not eliminate the contradiction, but only pushes it back. McTaggart argues that the only way to avoid contradiction is to eliminate the A-series, to accept that events do not really move from future to present to past. That passage is illusory, that reality consists only of the B-series, only of earlier-later relations. But the B-series without the A-series is not real-time, is only a static ordering, lacks the dynamism, lacks the passage that is essential to time. And so time is unreal, is an appearance that our consciousness generates from a fundamentally timeless reality. And McTaggart's position is a form of idealism about time, treats time as mind-dependent, as not part of the ultimate structure of reality. Visualize the paradox as a vicious circle. Events have A-series properties, but these properties are contradictory. So we index them to times, but then times have A-series properties, which are contradictory. So we index to second-order times, but these are contradictory, and the regress continues. And the contradiction is never eliminated, only relocated. And McTaggart concludes that the A-series is inherently contradictory, cannot be made coherent, and must be rejected. And with it goes time itself, which requires the A-series for its reality. One response to McTaggart's paradox, the tenseless or B-theory response, accepts McTaggart's argument that the A-series is contradictory, but denies that time requires the A-series, argues that the B-series is sufficient for real time, that earlier-later relations constitute time, and passage is an illusion, is a feature of our temporal perspective, and the universe exists as a four-dimensional block, a block universe where all times are equally real, and past, present, and future are not objective features of reality, but are indexical, are relative to a perspective. And this B-theory has become orthodoxy in philosophy of time, is widely accepted as avoiding McTaggart's paradox while preserving the reality of time. Another response, the tensed or A-theory response, denies that the A-series is contradictory, argues that McTaggart's argument involves a mistake, that A-series properties are not really contradictory because they are indexed to times in a non-problematic way, and the meeting being future at T1 and past at T2 is not contradictory, is just the normal way temporal properties work. And A-theorists argue that passage is real, that the present is objectively real, that the future is open and the past is fixed. And McTaggart's argument fails because it assumes that A-series properties must be simultaneous to be contradictory when they are not simultaneous, are at different times, and this response preserves the A-series, preserves passage, and rejects McTaggart's conclusion that time is unreal. A third response from presentism argues that only the present exists, that past and future are unreal, and so events do not have contradictory A-series properties because only present events exist, and only present properties are real, and the meeting is not simultaneously past, present, and future because only one of these is real at any time. And presentism avoids McTaggart's paradox by radical ontological restriction, by accepting that most of time does not exist, And this preserves the reality of the present, preserves passage, but faces difficulties explaining how truths about past and future can be true if past and future do not exist. McTaggart's paradox has been enormously influential, has shaped all debates about time, has forced philosophers to clarify their positions, to distinguish A theories from B theories, to recognize that different conceptions of time have different metaphysical commitments, and the paradox remains controversial, remains debated, with some accepting McTaggart's conclusion that time is unreal, some accepting that the A series is contradictory, but denying that this makes time unreal, and some denying that the A series is contradictory, and no consensus exists, and the paradox endures as one of the most important arguments in metaphysics, an argument that challenges our ordinary understanding of time, forces recognition that temporal passage, the movement from future through present to past, is philosophically problematic, and whether time is real or illusory remains one of philosophy's deepest questions. And McTaggart's paradox continues to structure the debate, continues to force philosophers to grapple with the nature of time, with whether passage is objective or subjective, with whether reality is a static four-dimensional block or a dynamic unfolding present, and the paradox persists, unsolved and perhaps unsolvable, a permanent challenge to theories of time. Inattentional blindness. Why a gorilla walks through your vision. Unseen. A person watches a video, follows instructions to count how many times basketball players wearing white shirts pass the ball, and they count carefully, focus on the white team, track the passes, and reach a final count. And then they are asked whether they noticed anything unusual, and they say no, nothing unusual, just basketball players passing the ball. And then they watch the video again, this time without counting, and they are shocked to see that a person in a gorilla suit walked through the middle of the scene, stopped in the center, beat their chest, and walked off. And this gorilla was visible for 9 seconds, passed directly through the action, was large and obvious, and yet the person did not see it the first time, was completely unaware, was blind to the gorilla despite looking directly at it. And this is inattentional blindness, demonstrated famously by Daniel Simons and Christopher Chabray in their invisible gorilla experiment, a phenomenon showing that attention is necessary for conscious perception, that we can look directly at something and not see it if we are not attending to it. And inattentional blindness reveals that perception is not simply determined by what falls on the retina, but is determined by what receives attention. And without attention, even salient obvious stimuli can be invisible, can pass unnoticed. And this challenges the idea that we consciously perceive everything in our visual field, shows that consciousness is limited to attended stimuli, and inattentional blindness has profound implications for understanding attention, consciousness, and the limits of awareness. Imagine the experience from the inside. You're focused on counting passes, tracking the white shirts, following the ball as it moves, and your attention is fully engaged, is consumed by the counting task. And the gorilla walks through, but you do not notice it. It does not register, does not enter consciousness. And the reason is that your attention is elsewhere, is focused on the white team. And the gorilla is not relevant to the task, is not expected, is not attended to. And without attention, the gorilla remains unconscious, remains invisible, despite being visible in the sense that the image falls on your retina, that your eyes are open and pointing at it. And this distinction between seeing with the eyes and seeing with attention reveals that conscious vision requires more than physical stimulation, requires attention, requires that processing reach a certain level. And inattentional blindness shows what happens when this does not occur, shows that stimuli can be physically present but mentally absent. Inattentional blindness differs from change blindness in that it occurs even without the need for comparison, occurs for stimuli that are continuously present, not just for changes, and the phenomenon shows that attention operates not just to encode changes, but to enable any conscious perception. And when attention is fully engaged elsewhere, when there is no spare attentional capacity, even salient, unexpected stimuli are missed, are not processed to the level of consciousness. And this demonstrates that attention is a limited resource, cannot be allocated to everything simultaneously, and when fully allocated to one task, nothing else reaches awareness, and the gorilla illustrates this dramatically, is an unexpected, salient stimulus that should capture attention, that would capture attention under normal circumstances. But when attention is fully engaged in counting passes, the gorilla is filtered out, is processed pre-consciously, but does not reach awareness. Visualize attention as a gate, and stimuli must pass through the gate to reach consciousness, and the gate is narrow, allows only a limited number of stimuli through, and when the gate is occupied by task-relevant stimuli, by the white-shirted players and the ball, irrelevant stimuli like the gorilla are blocked, are filtered out, and processing of the gorilla stops at an early stage, extracts basic features, but does not construct a conscious representation, and the gorilla remains invisible. And this gating model explains inattentional blindness, explains why stimuli that are physically present can be perceptually absent, because consciousness requires passing through the attentional gate, and only attended stimuli pass through. Inattentional blindness has practical implications for understanding accidents, for recognizing that drivers can look directly at pedestrians or other vehicles and not see them if attention is focused elsewhere. And looking is not the same as seeing. Vision requires attention, and when attention is engaged with navigation or conversation or phone use, stimuli outside the focus of attention can be missed, and this contributes to accidents, to collisions that seem inexplicable because the driver was looking, had clear sight lines, but did not see, did not notice the hazard. And understanding inattentional blindness is crucial for improving road safety, for recognizing the limits of human perception, and for designing systems that account for these limits. The phenomenon also has implications for understanding consciousness, for debates about whether consciousness requires attention, whether you can be conscious of unattended stimuli, and inattentional blindness suggests that consciousness requires attention, that unattended stimuli are not conscious, are processed unconsciously, and consciousness is limited to the small set of attended stimuli. And this supports the view that consciousness is sparse, is not the rich field of awareness we subjectively experience, but is a narrow spotlight that illuminates only what attention selects. And the subjective richness is an illusion, is created by the fact that attention moves rapidly, samples different regions, and wherever it lands, detail emerges. And we confuse this serial sampling with parallel richness, assume that because detail is available everywhere, it must be present everywhere. But inattentional blindness shows this is false, shows that unattended regions are not conscious, are invisible, even when physically visible. One response to inattentional blindness argues that some stimuli do capture attention automatically, do break through even when attention is engaged elsewhere, and highly salient or biologically significant stimuli like your own name or threatening faces or sudden loud noises capture attention, override current focus, and enter awareness. And this suggests that inattentional blindness is not absolute, is not a complete gate that blocks all unattended stimuli, but is a selective filter that allows some stimuli through based on salience and relevance. And the gorilla, while salient, is not personally relevant, not threatening, not expected, and so does not capture attention, does not override the counting task. And this response preserves some role for stimulus-driven attention, while acknowledging that inattentional blindness demonstrates the dominance of goal-directed attention. Another implication concerns legal contexts, concerns eyewitness testimony, and the reliability of visual reports. Because if people can miss large obvious stimuli like gorillas when attention is engaged elsewhere, then eyewitnesses can miss critical details of crimes, can fail to notice perpetrators or weapons or actions even when looking directly at the scene. And this challenges the assumption that eyewitnesses see everything, that memory failures are due to forgetting rather than to never encoding. And inattentional blindness shows that encoding requires attention, and attention is limited, and eyewitnesses cannot be expected to have noticed everything, and testimony must be evaluated with this in mind, must recognize the limits of attention and perception. The gorilla walks through the frame, visible and obvious, and yet unseen, unnoticed, invisible, due to inattention, due to the focus on counting passes, and the phenomenon reveals that consciousness requires attention, that seeing requires more than physical stimulation, requires cognitive engagement, requires processing resources that are limited, and when fully allocated elsewhere, nothing else reaches awareness, and the gorilla remains hidden. Hidden not by camouflage or occlusion, but by inattention, by the filter that protects consciousness from overload, that selects what matters and ignores the rest. And inattentional blindness endures as one of the most striking demonstrations in psychology, a phenomenon that challenges naive assumptions about perception, that shows the limits of awareness, that reveals consciousness as sparse and selective. And the gorilla continues to walk unseen through countless viewings, invisible to half the viewers, shocking to those who missed it. And the phenomenon persists, demonstrating that attention is the gateway to consciousness, and without attention, even gorillas are invisible. Fichte's paradox of knowability. There is an appealing idea in philosophy, a principle that seems to capture something important about truth and knowledge, and this is the knowability principle, which states that all truths are knowable, that for any true proposition, there is at least a possible situation in which someone knows that proposition, and this principle seems modest, even Platonic in spirit, suggesting that truth and knowledge are intimately connected, that reality is not fundamentally hidden or inaccessible, that the universe is intelligible in principle, even if not all truths are actually known by anyone at any given time. The principle distinguishes between what is known and what is knowable, acknowledging that many truths remain unknown, perhaps because no one has investigated them, or because the evidence is lost, or because the relevant questions have not yet been asked, but insisting that these unknown truths could be known, that there is no barrier in principle preventing them from being discovered. And this seems like a reasonable position, neither too strong like the claim that all truths are actually known, which is obviously false, nor too weak like the claim that some truths are unknowable, which seems to concede too much to skepticism and to suggest that reality contains secrets that are forever beyond our reach. But in 1963, Friedrich Fichte proved a shocking result, a theorem showing that if the knowability principle is true, then all truths are actually known, that the modest principle collapses into the absurdly strong claim it was meant to avoid. And this result, known as Fichte's paradox or the knowability paradox, has profound implications for epistemology, the philosophy of language, and debates about realism and anti-realism. And it forces philosophers to choose between giving up the knowability principle, accepting the absurd conclusion that all truths are known, or finding some way to reformulate the principle to avoid the paradox. The proof is elegant and surprisingly simple. Proceeding by reductio ad absurdum, suppose there is a truth that is unknown, call it P, and suppose also that no one knows that P is an unknown truth. That is, no one knows the conjunction P, and P is not known. And now apply the knowability principle, which says that this conjunction, being true, must be knowable, must be such that someone could know it. But here a contradiction emerges, because to know a conjunction, one must know both conjuncts. So to know P and P is not known, one must know P and also know that P is not known. But if one knows P, then P is known, which contradicts the second conjunct that P is not known. And so the conjunction P and P is not known cannot be known. It is an unknowable truth, and this contradicts the knowability principle, and therefore the assumption that there is an unknown truth must be false, and so all truths must be known. The paradox depends on the assumption that knowledge distributes over conjunction, that if you know P and Q, then you know P and you know Q, which seems uncontroversial, and on the assumption that knowledge is factive, that if you know P, then P is true, which is a standard requirement in epistemology, and so the paradox cannot be easily dismissed as relying on dubious principles. It seems to follow from our ordinary understanding of knowledge and knowability, and yet the conclusion is unacceptable. The claim that all truths are actually known is empirically false. There are obviously truths about the distant past, about the far reaches of the universe, about the inner workings of consciousness that no one knows. And so something must give, either the knowability principle or the reasoning that derives the paradox from it. One response is to reject the knowability principle, to accept that there are unknowable truths, truths that could never be known by anyone under any circumstances. And this is the position of semantic realists who argue that truth is independent of our capacity to recognize it, that reality outstrips our epistemic abilities, that the world contains facts that are forever beyond our ken. And for realists, the knowability paradox is not a disaster, but a vindication, a proof that the anti-realist commitment to knowability is untenable, that we must accept a more robust conception of truth as radically independent of knowledge. Another response, favoured by anti-realists and verificationists, is to reformulate the knowability principle to avoid the paradox while preserving the intuition that truth and knowability are connected, and various reformulations have been proposed. Some restrict knowability to propositions that do not involve knowledge ascriptions. Avoiding the problematic, self-referential structure of P and P is not known. Others distinguish between individual and collective knowability, arguing that all truths are knowable by the epistemic community as a whole, even if not by any single individual, and still others embrace a temporal or modal reformulation, claiming that all truths could have been known at some time or in some possible world, rather than claiming that all truths are actually knowable in all circumstances. Some philosophers argue that the paradox reveals a tension in the concept of knowability itself, that knowability is not a simple modal notion, but involves complex interactions between truth, knowledge, and the conditions under which knowledge is possible, and that our intuitions about these interactions are unreliable, pulled in different directions by competing commitments, and so the paradox exposes an instability in our conceptual scheme, rather than refuting any particular philosophical position. The paradox also connects to debates about the nature of propositions and the objects of knowledge. Because the problematic conjunction P and P is not known seems strange, it is a proposition about itself in a way, a proposition whose truth depends on whether it is known, and this self-referential or quasi-self-referential structure is reminiscent of the liar paradox and other semantic paradoxes, and some responses to Fitch's paradox draw on strategies developed for dealing with those paradoxes, such as hierarchies of languages, restrictions on self-reference, or non-classical logics that reject certain principles like the law of excluded middle. The paradox has implications for constructivism in mathematics and logic, because constructivists typically endorse some version of the knowability principle, identifying truth with provability or constructibility, and Fitch's paradox threatens this identification, suggesting that even constructivists must either accept that all mathematical truths are already proved, which is absurd, or abandon the simple identification of truth with provability and develop a more nuanced account of the relationship between the two. The knowability principle, innocent as it seemed, turns out to be a Trojan horse, a seemingly modest claim that conceals a radical commitment, and Fitch's paradox forces philosophers to confront the costs of various epistemological positions, to choose between realism with its unknowable truths and anti-realism with its need to reformulate or restrict the knowability principle. And the paradox remains a central puzzle in contemporary epistemology, a test case for theories of truth and knowledge, a proof that demonstrates with crystalline clarity that even the most intuitive principles can lead to absurdity when their logical consequences are rigorously traced. And it stands as a reminder that philosophy is not merely a matter of articulating and defending intuitions, but of following arguments wherever they lead, even when they lead to conclusions that undermine the very intuitions that motivated them. And the unknown truth, the proposition that is true but not known, sits at the center of the paradox, both knowable and unknowable, possible and impossible, a conceptual anomaly that refuses to be tamed by logic or softened by reformulation. And the paradox endures, a monument to the power of formal reasoning, to reveal deep tensions in our most basic concepts, tensions that no amount of philosophical maneuvering has yet managed to resolve in a way that satisfies all intuitions and preserves all principles. And so the debate continues, philosophers proposing new solutions, new restrictions, new interpretations, and the paradox persists, waiting to trap the unwary, to challenge the confident, to remind us that even truth and knowledge, the twin pillars of epistemology, are stranger and more problematic than they first appear. Epimenides' paradox. A poet from Crete named Epimenides once declared that all Cretans are liars, and this statement, simple as it seems, has echoed through the centuries as one of the earliest recorded paradoxes, a puzzle that predates even the formal study of logic, and yet contains within it the seeds of contradictions that still trouble philosophers today. If Epimenides himself is a Cretan and he claims that all Cretans are liars, then his statement must be a lie. But if his statement is a lie, then not all Cretans are liars, which means some Cretans tell the truth, which could include Epimenides himself, which means his statement might be true after all, which means all Cretans are liars, which means his statement is a lie and the cycle begins again. The paradox is not quite as airtight as the liar paradox that would emerge later, because calling someone a liar does not mean they always lie, only that they lie sometimes. And so there remains a sliver of logical escape, a possibility that Epimenides is telling the truth on this one occasion while still being a liar in general, or that his statement is partially true and partially false, depending on how it is interpreted. St. Paul referenced the paradox in his letter to Titus, quoting Epimenides and adding that the statement is true, seemingly unaware or unconcerned with the logical contradiction embedded in his endorsement. And this has led to centuries of theological and philosophical debate about what Paul intended and whether Scripture itself contains a paradox. The ancient Greeks recognized the puzzle, but lacked the formal tools to fully analyze it, treating it more as a rhetorical curiosity than a serious threat to logic. And it was not until the development of modern symbolic logic that the deeper implications became clear. The paradox belongs to a family of self-referential statements that collapse under their own weight, and Bertrand Russell would later use variations of this structure to reveal cracks in the foundation of mathematics, proving that not all sets can be safely defined, that not all statements can be assigned a truth value without contradiction. Some philosophers argue that the Epimenides paradox is weaker than its descendants because it depends on empirical facts about Cretans rather than purely logical structure, and that if we simply reject the premise that all Cretans are liars, the paradox dissolves, unlike the pure liar paradox which creates contradiction through its form alone. Others see it as an early recognition that language can turn against itself, that statements about truth and falsehood require careful handling, that self-reference introduces dangers that must be acknowledged and navigated. The paradox also raises questions about identity and generalization, about what it means to make sweeping claims about groups of people, and whether such claims can ever be fully coherent when the speaker is part of the group being described. Epimenides stands at the origin of a long tradition of logical puzzles, his words reverberating through time. A poet who may not have fully understood what he had unleashed, but who nevertheless gave voice to one of the fundamental tensions in human thought, the way that truth can fold back on itself and become strange, unstable, uncertain. Gabriel's horn paradox, a three-dimensional solid of revolution, is formed by taking the curve y equals 1 over x, for x greater than or equal to 1, and rotating it around the x-axis, and this creates a shape that resembles a horn or a trumpet, wide at one end near x equals 1, and tapering endlessly as x increases toward infinity, growing ever narrower but never closing, extending infinitely far in one direction. And this shape is called Gabriel's horn, named after the archangel whose trumpet signals the end of days. And the paradox is that this infinite horn has finite volume but infinite surface area. And this seems contradictory, or at least deeply strange, because if the volume is finite, then you could fill the horn with a finite amount of paint, but if the surface area is infinite, then you would need an infinite amount of paint to coat the surface. And so it seems that you can fill the horn, but cannot paint it. And this apparent impossibility is Gabriel's horn paradox. The mathematics is straightforward. The volume of the horn is calculated using the formula for volumes of revolution, integrating from 1 to infinity the area of circular cross-sections. And the cross-section at position x has radius 1 over x, and so the area is pi times 1 over x squared. And integrating this from 1 to infinity gives pi a finite volume, meaning the horn could contain pi cubic units of liquid. And the surface area is calculated using the formula for surface area of revolution, integrating the circumference of each cross-section multiplied by an element of arc length. And this integral diverges. It grows without bound as the upper limit of integration increases, and so the surface area is infinite. And this combination, finite volume and infinite surface area, is what creates the paradox. The resolution of the paradox lies in recognizing that paint, as a physical substance, has thickness. It is not a mathematical surface with zero thickness, but a three-dimensional coating. And if the paint has any positive thickness, however small, then painting the inside of the horn requires filling a three-dimensional region, not just covering a surface, and the volume of this region is finite because it is contained within the horn, which has finite volume, and so a finite amount of paint suffices to coat the inside to any specified thickness, and the paradox dissolves. The apparent impossibility is an artifact of treating paint as if it were a zero-thickness mathematical surface, when in reality it is a substance with volume. Another way to see the resolution is to note that the distinction between filling and painting is not as sharp as it seems. Filling the horn means occupying its entire interior volume, while painting the surface means adding a thin layer. But if the layer has thickness, then painting is a form of filling a thin shell around the surface, and since the horn has finite volume, any shell within it also has finite volume, and so painting, properly understood, requires only a finite amount of paint. And the paradox arises from conflating mathematical surface area, which can be infinite, with physical coating, which requires volume, and volume is finite. Gabriel's horn also raises questions about the nature of infinity in geometry, about what it means for a geometric object to be infinite, and whether infinite objects can have finite properties, and the horn shows that they can. That infinite extent in one dimension, length, is compatible with finite extent in another dimension, volume, and this is not unique to the horn. Many geometric objects exhibit similar behavior: infinite regions with finite area, infinite surfaces with finite curvature. And these examples show that infinity is not a single uniform concept, but comes in degrees and dimensions, and that intuitions about finite objects do not always transfer to infinite objects. The paradox also appears in discussions of limits and convergence, because the volume integral converges to a finite value while the surface area integral diverges. And this difference reflects the rates at which the integrands decrease as x increases. The volume integrand decreases like 1 over x squared, fast enough that the sum over an infinite range is finite, while the surface area integrand decreases like 1 over x, not fast enough to produce a finite sum. And this distinction between different rates of decay is central to analysis and calculus, determining which infinite series converge and which diverge, which integrals are finite and which are infinite. Some philosophers and mathematicians have used Gabriel's horn to argue about the nature of mathematical existence, about whether infinite objects like the horn really exist or are merely useful fictions, because the horn cannot be physically realized. No physical material extends infinitely, and no physical process could construct an infinite shape. And so, the horn is an idealization, a mathematical abstraction, and the paradox, if it is one, is a feature of this abstraction rather than a claim about physical reality. And this raises the question of whether mathematical paradoxes reveal truths about an independent mathematical realm or merely expose the limits of our abstractions and idealizations. Gabriel's horn has also been used in pedagogy to teach students about improper integrals, about the difference between convergence of volume and surface area, about the importance of careful calculation and the dangers of relying on intuition. And the paradox is memorable. It sticks in the mind, a striking example that challenges assumptions and forces students to think carefully about what integration measures and what infinity means. And for these reasons, the horn remains a staple of calculus courses, a classic example that generations of students have encountered and puzzled over. The horn extends to infinity, narrowing as it goes, its volume contained, its surface spreading without bound. And the paradox asks whether this makes sense, whether an object can be filled but not painted. And the answer is that paint has thickness, that coating requires volume, that mathematical surfaces and physical substances are different, and that the paradox is resolved by attending carefully to what filling and painting actually mean. And the horn remains a beautiful and strange geometric object, a shape that embodies the counterintuitive properties of infinity, a reminder that infinite objects do not behave like finite objects scaled up, but follow their own logic, their own rules, and that intuition trained on the finite is an unreliable guide to the infinite. And Gabriel's horn sounds on, infinite in reach but finite in substance, a paradox that is no paradox once understood, a puzzle that teaches about integration, about infinity, about the relationship between mathematical idealization and physical reality, and about the need to distinguish between what can be calculated and what can be realized, between the abstract and the concrete, between the mathematical and the material. And the horn remains a fixture in mathematics, a lesson in calculus, a paradox that resolves itself once the terms are clarified, once the mathematics is understood, once the nature of paint and surfaces and volume is properly considered, and the paradox fades, leaving behind understanding, leaving behind a deeper appreciation for the subtleties of infinite geometry, and for the care required when reasoning about objects that extend without end. Frankfurt's counterexamples. When you're responsible. Even though you had no choice, a person decides to perform an action, decides on their own, without coercion, based on their own reasons and desires, and they perform the action, and we say they are morally responsible. They acted freely. They deserve praise or blame for what they did. And traditional theories of moral responsibility say that responsibility requires the ability to do otherwise, requires that the person could have chosen differently, that they had genuine alternatives. And this principle, called the principle of alternate possibilities, seems obvious, seems essential to responsibility, because how can you be responsible for an action if you had no choice? if you were forced to do it, if no alternative was possible. And yet philosopher Harry Frankfurt constructed examples that challenge this principle. Examples where a person acts on their own, makes their own decision, but could not have done otherwise, and yet intuitively seems responsible. And these are Frankfurt's counterexamples. Thought experiments designed to show that the principle of alternate possibilities is false. That responsibility does not require the ability to do otherwise, that what matters is how you acted, whether the action flowed from your own will, not whether you could have acted differently. And Frankfurt's cases have been enormously influential, have reshaped debates about free will and responsibility, have challenged incompatibilist arguments that say determinism undermines responsibility, and the counterexamples remain controversial, remain debated, but have permanently changed the landscape of discussions about freedom. Imagine the example: a person named Jones decides to perform an action, decides to vote for a certain candidate, and Jones makes this decision on his own, based on his own political views, his own deliberation. No one forces him, no one coerces him, and he goes to vote, and he is about to vote for the candidate he chose. And at this moment, unbeknownst to Jones, there is another person, call him Black, who has been monitoring Jones's brain states, and Black has the ability to intervene, to manipulate Jones's brain, to force Jones to vote for the candidate if Jones shows signs of changing his mind. And Black is prepared to intervene, but does not need to, because Jones votes for the candidate on his own, makes the decision himself, and Black's intervention mechanism remains dormant, unused. And the question Frankfurt asks is whether Jones is morally responsible for his vote. And intuitively, the answer is yes. Jones voted based on his own decision, his own reasons. Black's presence made no difference. Black did nothing, and Jones is responsible just as he would be if Black did not exist. And yet Jones could not have done otherwise, because if he had tried to vote differently, Black would have intervened, would have forced him to vote for the candidate. And so Jones had no alternative, could not have avoided voting as he did, and yet he is responsible. And this shows that responsibility does not require the ability to do otherwise, that the principle of alternate possibilities is false. The structure of Frankfurt cases involves two elements. The person acts on their own, based on their own will, their own reasons, and there is a counterfactual intervener, someone or something that would have prevented any alternative action, that ensures the person does what they do. But the intervener does not actually act, remains dormant, and so the person's action is their own, even though alternatives were blocked. And Frankfurt argues that what matters for responsibility is not whether alternatives existed, but whether the person acted on their own, whether their action flowed from their own will. And in Frankfurt cases, the action does flow from the person's own will, and so they are responsible even though they could not have done otherwise. Visualize moral responsibility as depending on the actual sequence, on how the action was actually produced, rather than on alternative sequences on what might have happened. And in Frankfurt cases, the actual sequence is normal. The person deliberates and chooses and acts, while alternative sequences are blocked by the intervener. And since responsibility depends on the actual sequence, the person is responsible, and the blocked alternatives are irrelevant. And this shows that incompatibilists are wrong to think that determinism, by ruling out alternatives, undermines responsibility, because even if determinism rules out alternatives, as long as people act on their own, based on their own reasons, they are responsible, and responsibility is compatible with determinism. Critics of Frankfurt cases have offered various objections. One objection denies that the person really lacked alternatives, argues that in Frankfurt cases there are flicker alternatives, tiny alternatives, that remain open until the very last moment, moments where the person could begin to choose differently before the intervener stops them, and these flickers are enough to preserve the principle of alternate possibilities, enough to ground responsibility. And so Frankfurt cases do not refute the principle, only show that responsibility does not require robust alternatives, only requires minimal alternatives, tiny flickers of freedom. Another objection questions whether Frankfurt cases really elicit the intuition that the person is responsible, argues that when we imagine the cases carefully, when we recognize that the person truly could not have done otherwise, our intuition of responsibility weakens. And maybe Jones is not fully responsible. Maybe the presence of Black's intervention mechanism, even though unused, affects responsibility, creates a situation where praise and blame are inappropriate, and this response denies that Frankfurt cases generate clear counterexamples, argues that intuitions are unclear or support the principle of alternate possibilities rather than undermining it. A third objection distinguishes between moral responsibility and blameworthiness, argues that Frankfurt cases might show that people can be causally responsible, can be the source of an action, even without alternatives. But this does not show they are morally responsible, does not show they deserve blame or praise, and moral responsibility requires more than being the source of action, requires the ability to do otherwise, requires that the person had control, and Frankfurt cases do not establish moral responsibility, only causal responsibility. Frankfurt has refined his examples over decades, responding to objections, constructing new variants, and the debate continues, with defenders arguing that Frankfurt cases successfully refute the principle of alternate possibilities, show that compatibilism is correct, that responsibility does not require alternatives, and critics arguing that the cases are flawed, that intuitions are unclear, that responsibility does require alternatives after all, and no consensus has emerged. But Frankfurt's contribution is undeniable, has forced philosophers to clarify what responsibility requires, to distinguish between different kinds of freedom, different kinds of control, and to recognize that the relationship between determinism and responsibility is more complex than simple, incompatibilist arguments suggest. Frankfurt's counterexamples also connect to debates about moral luck, about whether responsibility depends on factors beyond our control. Because in Frankfurt cases, the person is responsible, even though whether alternatives were available was beyond their control, was determined by Black's presence. And this suggests that responsibility is not undermined by factors beyond our control, is not sensitive to luck, and what matters is the actual sequence, how the person actually acted, not whether they were lucky enough to have alternatives. Jones stands in the voting booth, marks his ballot, and Black watches, does nothing, and Jones is responsible, is praised or blamed for his vote, and yet he could not have voted otherwise. And Frankfurt's case challenges traditional assumptions, challenges the principle of alternate possibilities, and forces recognition that responsibility is about actual causation, about whether the person's will was effective, not about whether alternatives existed. And Frankfurt's counterexamples endure as some of the most important thought experiments in philosophy of action, examples that reshaped debates about free will, that challenged incompatibilist arguments, that supported compatibilism, and that remain controversial, remain debated, but have permanently influenced how philosophers think about moral responsibility, about what it requires, about whether determinism threatens it, and the counterexamples persist as permanent features of the landscape, cases that every theory of responsibility must address, must accommodate or explain away. And Frankfurt's legacy includes these cases, these examples that showed that responsibility might not require what we thought it required, might not depend on alternatives, but on something else, on source, on causation, on whether the action flows from the agent's own will. And the debate continues, and Jones votes, and Black does nothing, and the question remains whether Jones is responsible, and Frankfurt says yes. And the counterexamples stand, challenging, probing, revealing complexity in concepts we thought were simple. Laplace's demon, the mind that knows everything, that will ever happen. A supremely intelligent being, a vast intellect that knows the position and velocity of every particle in the universe at a single instant, stands outside time and space. And this being, this demon, as Pierre-Simon Laplace called it in 1814, possesses the complete laws of physics, the equations that govern how particles interact and move, and with this information, the precise state of every atom and the exact rules of motion. The demon can calculate the future, can determine with perfect accuracy where every particle will be at any future time, can predict every event, every thought, every decision, every outcome, from the fall of a raindrop to the rise of civilizations, from the collision of atoms to the death of stars. And in principle, the demon could also calculate the past, could trace every particle's trajectory backward to determine exactly how the present arose from previous states. And so this demon, given sufficient computational power, could know everything that has happened and everything that will happen. The entire history of the universe, past and future, encoded in a single snapshot of the present. And this is Laplace's demon, a thought experiment about determinism, about whether the universe is a clockwork mechanism, where the future is entirely determined by the past, where free will is an illusion, where everything that will ever happen is already decided, already implicit in the current state of things. Imagine the demon's knowledge as a vast table, infinitely long, listing the position and velocity of every particle, every electron, every quark, every photon, trillions upon trillions upon trillions of entries, and the demon has access to all this information perfectly, knows it exactly, with infinite precision. And the demon also knows Newton's laws, or perhaps Einstein's field equations, or quantum mechanics, knows the rules that govern how these particles influence each other, how forces propagate, how energy transfers. And with this knowledge, the demon can simulate the universe, can run the equations forward in time, calculating step by step how the particles will move, how they will collide and interact, and the simulation produces a prediction, a complete specification of the universe at every future moment. And this prediction, if the laws of physics are deterministic, is not probabilistic but certain. The future is determined, fixed, inevitable, and the demon knows it all. The implications are profound and troubling, because if Laplace's demon is possible, if the universe is deterministic, then free will becomes problematic, becomes perhaps an illusion, because every decision you make, every thought you have, every action you take is the result of particles in your brain following physical laws, and those particles are moving according to rules determined by their initial conditions, and those initial conditions were set by earlier states, going back to the beginning of the universe. And so your choices are not free but predetermined, decided billions of years ago when the universe began, and you are not an agent but an automaton, a complex machine that operates according to fixed rules. And the feeling of making choices, of deliberating and deciding, is a subjective experience produced by computational processes in your brain. But the outcome was never in doubt, was determined from the start. And this conclusion undermines moral responsibility, undermines the concepts of praise and blame, undermines the notion that people could have done otherwise, and it raises the question of what it means to be human if our actions are all predetermined. But Laplace's demon faces several obstacles, several reasons why even in principle it might be impossible. The first obstacle is quantum mechanics, which was unknown in Laplace's time, but is now recognized as fundamental to physics, and quantum mechanics is probabilistic, not deterministic. The Heisenberg uncertainty principle states that we cannot know both the position and velocity of a particle with perfect precision. There is an irreducible indeterminacy, a fundamental limit on what can be known, and when we measure a quantum system, the outcome is random, governed by probabilities but not determined. And so Laplace's demon cannot have the precise initial conditions it needs, cannot know the exact state of the universe, and even if it could, the laws of quantum mechanics only predict probabilities for future events, not certainties, and so the future is genuinely open, not determined, and Laplace's demon is impossible. The second obstacle is chaos sensitivity to initial conditions, where tiny unmeasurable differences in starting states lead to vastly different outcomes over time. Weather systems, planetary orbits, fluid flows, all exhibit chaotic behavior, where prediction becomes impossible beyond a certain time horizon, because errors in measurement, no matter how small, grow exponentially and eventually dominate. And even if quantum mechanics were not an issue, even in a classical deterministic universe, practical prediction would be impossible for chaotic systems, and the demon would need infinite precision, infinitely accurate knowledge of initial conditions, and any finite approximation, no matter how good, would fail after sufficient time, and so the demon's predictions would be useless for complex systems on long time scales. The third obstacle is computational. Even if the demon had perfect information and deterministic laws, simulating the universe requires computing power, requires processing the interactions of every particle, and the universe contains roughly 10 to the 80 particles, and computing their evolution requires resources, and some physicists have argued that simulating the universe would require a computer as large as the universe itself, and such a computer could not run faster than the universe it simulates, could not predict the future faster than the future unfolds. And so the demon could not tell you tomorrow's events before tomorrow arrives, and the demon becomes useless as a predictor, reduced to a mere recorder that reconstructs what has already happened, rather than foretelling what will happen. Visualize the universe as a vast machine, gears turning, particles moving, and Laplace's demon standing outside, watching the machine, knowing the position of every gear, the velocity of every component, and calculating how the machine will continue to turn. But the demon is blocked by quantum uncertainty, cannot measure the gears precisely enough, is blocked by chaos, cannot maintain accuracy over time, is blocked by computational limits, cannot perform the calculation fast enough, and so the demon, mighty as it seems, is impossible. The universe resists total prediction, resists complete knowledge, not because of practical limitations, but because of fundamental features of physical law and determinism. Even if it were true, does not grant us the power to predict. And the demon remains a thought experiment, a symbol of a kind of knowledge that cannot exist, a vision of omniscience that is ruled out by the nature of reality itself. Laplace's demon also raises philosophical questions about explanation and understanding, because even if we cannot predict the future, even if determinism fails or the demon is impossible, we still seek to explain why things happen, to trace causes and effects, to understand the mechanisms that generate events. And this explanatory project does not require Laplacian determinism, does not require perfect prediction, but only patterns, regularities, laws that hold approximately, and science proceeds without the demon, without omniscience, by finding partial explanations, probabilistic models, statistical regularities, and these are sufficient for understanding, for technology, for navigating the world, and the demon's impossibility does not doom science but liberates it, frees it from the burden of total prediction, allows it to focus on what can be known rather than lamenting what cannot. The demon sits in conceptual space, all-knowing and impotent, knowing everything but unable to act, unable to exist, blocked by uncertainty, by chaos, by computation, and Laplace's vision of a deterministic clockwork universe fades, replaced by a more subtle picture, a universe governed by laws but not wholly determined, open to chance, to randomness, to emergence, where the future is not written in the present but unfolds through processes that are partly lawful and partly random, and free will, though not proven, is at least not obviously refuted, and moral responsibility, though challenged, survives because even if determinism were true, Even if all actions are caused by prior states, we still distinguish between actions that flow from deliberation and those that do not, between agents who respond to reasons and those who do not, and these distinctions matter. Ground our practices of praise and blame, and Laplace's demon, impossible and paradoxical, remains a touchstone in debates about determinism, free will, and the limits of knowledge. A thought experiment that has shaped centuries of discussion and continues to challenge our understanding of what it means to predict, to know, and to be free. Hilbert's Hotel Paradox. A hotel with infinitely many rooms, each numbered with a positive integer, 1, 2, 3, and so on without end, stands fully occupied. Every room contains a guest, and yet when a new guest arrives, the manager is not concerned, does not turn them away, because infinity accommodates addition in ways that finite quantities cannot. And the manager simply asks each current guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on, each guest shifting one room higher. And this process, applied simultaneously to all guests, leaves room 1 vacant, and the new arrival is accommodated without displacing anyone permanently. And this is Hilbert's Hotel, a thought experiment devised by the mathematician David Hilbert to illustrate the counterintuitive properties of infinite sets, to show that infinite collections behave in ways that violate ordinary intuition, that they can be put in one-to-one correspondence with proper subsets of themselves, that adding elements or removing elements does not change their cardinality, and that the whole is not always greater than the part when dealing with infinity. The paradox deepens when an infinite number of new guests arrive, an infinite bus pulling up to the hotel, each passenger needing a room. And again, the manager is unperturbed, because there is a strategy to accommodate everyone. The manager asks each current guest in room N to move to room 2N. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6, and so on. And this process places all the original guests in the even-numbered rooms, leaving all the odd-numbered rooms vacant. And since there are infinitely many odd-numbered rooms, one for each positive integer, there is exactly enough space for the infinitely many new arrivals, who are assigned to rooms 1, 3, 5, and so on. And the hotel, despite being full, has accommodated an infinite number of additional guests without anyone being displaced. The paradox reveals that infinite sets have a property called countable infinity. They can be placed in one-to-one correspondence with the natural numbers, and this correspondence allows for operations that seem impossible with finite sets. A fully occupied hotel with finitely many rooms cannot accommodate additional guests without evicting someone. But a fully occupied hotel with infinitely many rooms can accommodate not just one additional guest, but infinitely many. And this does not mean the hotel was not really full before. All rooms were occupied, but rather that fullness does not prevent expansion when infinity is involved, that the concepts of full and empty take on new meanings in the infinite context. Hilbert's Hotel also allows for even stranger scenarios. Suppose infinitely many infinite buses arrive, each bus containing infinitely many passengers, and the hotel must accommodate all of them. And again, there is a strategy. The manager can use a pairing function, a mathematical technique that assigns a unique room number to each combination of bus number and seat number, ensuring that every passenger gets a unique room. And the hotel, starting from full occupancy, can expand to accommodate not just countably many new guests, but countably many groups of countably many new guests. Because the union of countably many countable sets is still countable, and so the total number of guests, after all the buses are accommodated, is the same cardinality as the number of guests before. Both are countably infinite. Both can be placed in one-to-one correspondence with the natural numbers. The paradox challenges intuitions about size, quantity, and comparison, because it shows that infinite sets can be proper subsets of themselves, and yet have the same cardinality. The even numbers are a proper subset of all natural numbers, missing all the odd numbers, and yet there are just as many even numbers as natural numbers. Both sets are countably infinite, and this violates the Euclidean principle that the whole is greater than the part, a principle that holds for finite sets but fails for infinite sets. And this failure is not a contradiction, but a distinctive feature of infinity, a marker that distinguishes finite from infinite. Hilbert's Hotel also raises questions about the physical realizability of actual infinities, because while the mathematics of infinite sets is well defined and consistent, whether actual infinite collections exist in the physical world is contested. Some philosophers and physicists argue that only potential infinities exist, processes that can continue indefinitely but never reach completion, while actual infinities, completed infinite totalities, are merely mathematical. Abstractions and the hotel paradox, with its fully occupied infinite structure, represents an actual infinity. And if such infinities cannot exist in reality, then the paradox is merely a mathematical curiosity without physical significance. But others argue that the universe may be spatially infinite, that time may extend infinitely into the past or future, and that quantum field theory involves infinite dimensional spaces. And if actual infinities are physically real, then the strange properties illustrated by Hilbert's Hotel may have real-world counterparts. The hotel also appears in theological discussions about divine attributes, because an omnipotent being might be thought to perform tasks that involve manipulating infinite collections. And Hilbert's Hotel shows that such manipulations are logically coherent, that infinity does not lead to contradiction, that an infinite hotel can be fully occupied and yet accommodate more guests. And this addresses worries that infinity is inherently paradoxical or incoherent, demonstrating that infinite structures follow consistent rules, even when those rules differ from finite intuitions. The hotel stands infinitely tall, infinitely long, each room numbered, each room occupied, and the new guest arrives. And there is room, always room, because infinity plus one is infinity, because infinity plus infinity is infinity, because the operations of addition and union that exhaust finite resources leave infinite resources unchanged, and the paradox reveals the strangeness of infinity, the way it defies expectation, the way it makes possible what seems impossible. And Hilbert's Hotel remains one of the most vivid and accessible illustrations of this strangeness, a story that captures in simple terms the profound weirdness of the infinite. And mathematicians use it to teach, to explain cardinality, to distinguish countable from uncountable infinities, to motivate Cantor's diagonal argument and the hierarchy of infinities. And philosophers use it to probe intuitions about existence, about the difference between actual and potential infinity, about whether the physical world contains or could contain infinite structures. And the hotel endures, a fictional place that illuminates real mathematics, a thought experiment that has become a permanent fixture in discussions of infinity, a paradox that is not a contradiction, but a revelation, a demonstration that infinity is not merely a large finite number, not merely an extension of ordinary quantity, but something qualitatively different, something that requires new concepts, new intuitions, and new ways of thinking about size, about number, about what it means for something to be more or less equal or unequal, full or empty. And the guests check in, infinitely many guests, and there is always room for more.